Hi, I'm Mrs. Edwards, and today we're going to go through a problem that I like to call the calculus-loving dog problem. You're going to learn the difference between an average rate of change and an instantaneous rate of change. And we're going to be using these average rates of change to estimate the instantaneous rate of change. This is a key lesson that I will often refer back to, so remember it is called the calculus-loving dog problem. We'll refer back to it often, not because of all the calculus that we're going to do in this lesson, but because of the conceptual understanding we are about to develop. Instantaneous rate of change is known in calculus as the derivative. This is the topic we spend almost the entire first half of the class on. So it's important that you walk away knowing what a derivative is. So let's get to it. Say you and your calculus-loving dog are hanging out one day and you decide to drop a ball out of your 10th story window. Here's the formula that's going to tell you how far the ball has dropped after a given number of seconds. My physics people, we are ignoring air resistance. So h of t equals 16t squared. Let's take a look at the graph of this function and investigate it just a little bit. Our calculus-loving dog is saying, I wonder how fast the ball is going at exactly 1 second. So let's take a look at the graph. On our x-axis, the time there is going to be the time since the ball was dropped in seconds. On the y-axis, the h of t, that's going to represent the distance that the ball has fallen in feet. Here's a graph. Let's look at just a couple of points. 0, 0, for example, means that at time 0 seconds, the ball has dropped a distance of 0 feet. At 1 second, if I substitute 1, h of 1 is going to equal 16. So at 1 second, the ball has dropped a distance of 16 feet. So keep in mind the answers that we're getting to this when we substitute a number in, it's not the distance the ball is off the ground, it's the distance the ball has dropped. So at 2 seconds, for example, if I substitute 2, h of 2, 16 times 2 squared is 64. So after 2 seconds, the ball has dropped a distance of 64 feet. Notice that it also dropped a lot further in from the time 1 to 2 seconds. From time 0 to 1 second, it only dropped 16. And so from 0 to 2 seconds, it was 64, which means in that second, it dropped 48 feet. The reason that's happening is because the ball is traveling faster and faster and faster as time goes on. Ultimately, we want to answer the question that the calculus dog is presenting us. How fast is the ball traveling at exactly 1 second? But if we use the math that you know up to this point, you don't know any calculus to speak of. We're starting to learn about limits, but you don't know a lot of calculus yet. If we start to use some of the math that you know up to this point, a formula that might come to mind is the DIRT formula. Distance equals rate times time. If we solve for rate by dividing both sides by time, then we could find maybe rate with distance divided by time. But this is the total distance divided by time. So let's look at these couple of points, and then we'll use our y sub 2 minus y sub 1 to get the total distance, and x sub 2 minus x sub 1 for the amount of time it took to travel that distance. So using our formula here, we end up getting 16 feet per second. This is the secant line to the curve. That is 16. And so the first important concept is if you find the slope between 2 points, which is your secant line, you are finding the average rate of change. This is not how fast the ball is going at 1 second. This is how fast the ball is going on average. So from 0 to 1 second, the average speed of the ball was 16 feet per second. The ball, as we said, is dropping faster and faster and faster. So at say 0.1 seconds compared to 0.9 seconds, at 0.9 seconds, the ball is going faster than it was at 0.1 seconds. So this is taking into account all of those different speeds from 0 to 1 second, and it's the average over that course of time. I'm going to take one moment here and focus on the word speed. Speed is the absolute value of velocity, and you should take a moment and write that down, that speed is the absolute value of velocity. Here we have the speed is 16 feet per second, but the velocity of the ball is negative 16 feet per second. The only difference between velocity and speed is that for velocity, direction matters. So since the ball was falling, that's what makes the velocity negative 16 feet per second. If, for example, we threw the ball in the air, that first second where it's going up, well, then maybe the velocity would be positive 16. We're just making up a number there. But if it was going up, velocity is positive, down, velocity is negative. But speed, since it's the absolute value of velocity, it's just 16 feet per second. Okay, ultimately what we're trying to find is how fast is it going at exactly 1 second. So do you think that this is an overestimate or is it an underestimate? Well, since it contains the speeds as the ball's going faster, 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 and it's containing the times when the ball was moving slower, by the time we get to 1 second, that's the fastest that it had gone on the interval 0 to 1. So this 16 feet per second is an estimate of how fast it's going at 1 second, but it is an underestimate. Let's look at possibly finding an overestimate. Using the same dirt formula, distance divided by time, if I stick with using 1/16 because I care about what's happening at 1 second, but I use a point on the other side of the curve, and I make my calculation here. Now I'm going to start using a little bit better notation. Instead of y sub 2 minus y sub 1 over x sub 2 minus x sub 1, we're going to use this notation because this is the notation that you're going to start seeing. So h of 2 simply means we're substituting 2 in. 16 times 2 squared is 64. So that's 64 is going to be here. And then h sub 1, if I substitute in 1, 16 times 1 squared is 16. So this is 16. Okay, so just one more time there. All right, simplifying, and I come out with 48. So I'm going to draw that in, and the secant line, the slope of that secant line is 48. What we have just found is that from 1 to 2 seconds, the average speed of the ball is 48 feet per second. So over the time interval 0 to 2 seconds, even though the ball is falling faster, 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 on average, it was going 48 feet per second. But thinking about that time interval from 1 to 2 seconds, at 1 second, the ball was going the slowest compared to all of the speeds on the interval 1 to 2 seconds. So this is going to end up being an overestimate. Quick review of speed. So the speed here is 48 feet per second, but the velocity of the ball on average was negative 48 feet per second. All right, keeping our eye on the ball, we're trying to find the speed of the ball at precisely 1 second. We currently have fixed that point, 1, plugged in 1 comma 16. We selected a point to the left of 116 on the curve, and we calculated the slope of the secant line, and we found out that that was 16 feet per second. We stayed with 1 second, and then we grabbed another point on the curve to the right of that point, calculated the slope of the secant, and we ended up getting 48 feet per second. And so we have an underestimate and we have an overestimate for how fast the ball is going at precisely 1 second. So what is it going to be at 1 second? We have an overestimate and an underestimate. Well, let me show you graphically what that is. If I show this graphically at 1 second, if I draw in a tangent line at 1 second, the slope of that tangent line is how fast the ball is going at 1 second. That is a really, really key idea here. The slope of the tangent is instantaneous rate of change. That is a calculus topic. At the beginning, I said that we're going to be studying derivatives for nearly the first half of the class. And the slope of a tangent line, that is what a derivative is. The derivative of the function 16t squared evaluated at 1 is the slope of that tangent line. Currently, what we're doing is we are using the average rates of change to estimate what is the slope of that tangent line, the instantaneous rate of change. And we know right now that the slope of this tangent line is greater than 16, but less than 48. So, can we do better? Well, I think we can. Let's start with that same coordinate, 116. We're always starting with 1 because we're trying to figure this out at 1 second. But instead of picking a point over here, let's pick a point closer to 116. So if I substitute in a half a second, 16 times a half squared is 4. Let's calculate the slope of that secant line again. And we end up getting 24 feet per second. This is from 0.5 seconds to 1 second, the average speed of the ball. And this again is an underestimate because by the time we get to 1 second, it's going the fastest. So then we've just found the average speed from a half a second to 1 second. So we do know, though, that it is greater than 24, and we used to only know it was greater than 16. Just a reminder, the velocity of the ball is negative 24 feet per second because it's falling. All right, let's try this from the other side. Fixing that point, 116. Let's select another point, even closer to 116, but from the right-hand side. So let's calculate the slope of the secant line. We end up getting 40, so that means that from 1 to 1.5 seconds, the average speed of the ball was 36 feet per second. Since this time interval is 1 to 1.5, and at 1 second, the ball would be going the slowest on the time interval 1 to 1.5. This average rate of change from 1 to 1.5 is going to be an overestimate. This is the same thing as saying that the average rate of change from 1 to 1.5, the average velocity is negative 40 feet per second. Okay, let's recap what we've done here to estimate the instantaneous rate of change at time 1 second. In other words, how fast it's going at 1 second. We began by fixing the point 116. We're fixing that point because we want to know at 1 second. Then we selected a point close to 1 on the left. So we used x equals 0. We calculated the slope of the secant, which was 16. Next, we stayed with the coordinate 116, picked a point even closer to 1 on the left of 1. So we went with 0.5, calculated the slope of the secant line. We got 24. Both of these are underestimates, but 24 is a better underestimate. The reason it is a better underestimate is also because it's a point that we selected that's closer to 116. Then we kept the 116 and started looking for overestimates. We picked 2, which is on the right side of 1, calculated the slope of the secant and got 48. Stayed with 1, 16, picked a point even closer to the point 116 on the right side. We plugged in 1.5, calculated the slope of the secant and got 40 feet per second. And so ultimately we can answer our calculus-loving dog who said, I wonder how fast the ball is traveling at 1 second. We can at least estimate here. We know that it's going to be greater than 24 and less than 40. So I'm going to say, oh, I think it's about 32 feet per second. We're using slope of secant lines to estimate the slope of the tangent. We could get an even better approximation over and over again by moving these 2 points here closer and closer to 116. You might go with using 0.9 and go with 0.9 to 1 second and 1.1 second, 1 second to 1.1 seconds. And then these two values, still being over and under estimates, would be super, super close together, and it would be much easier to see that the slope of this tangent is actually 32 feet per second. I think our calculus-loving dog, loving calculus and all, wants to adjust his question. Perhaps he wants to know, I wonder what the velocity of the ball is at 1 second. Well, the velocity would be negative 32 feet per second. So let's go over all of the big takeaways from this example. Let's say that we name our function f of x instead of h of t. So we have our function f of x. We know that speed is the same thing as the absolute value of velocity. So that's one thing we know. Some other big ideas. Average rate of change is the same as finding the slope of the secant line, which is the same as using the formula f of b minus f of a over b minus a. All of these topics over here, these are all the exact same thing. Those go together. So if you had a question that said, find the slope of the secant line, or find the average rate of change between these two times, this is what you're using. Okay, on the other side here, instantaneous rate of change. How fast something is going at exactly 1 moment in time. That is the slope of the tangent. That is the derivative. All of these things mean the same thing. Instantaneous rate of change, slope of the tangent, derivative, velocity, those all mean the same thing. And then the notation in calculus, if our function is called f of x, if we take the derivative, if we found the slope of the tangent, if we found the instantaneous rate of change, that is f prime is the way you read that, f prime of x. In your homework tonight, you will have to find some average rates of change. You'll also be doing some story problems that are similar to the one we went over. But let's just take the story problem out of it for a second and say, find the average rate of change of this function over the given interval. So here is a graph of h of t equals 16t squared. And if we're on the interval 1 to 2, that means that we're going from x is 1 to x is 2. I substituted those numbers. And we know that average rate of change means the slope of the secant line. Thinking of our notation from the past, we might write that, but let's not. Let's use some really good notation and say h of 2 minus h of 1 over 2 minus 1, which equals this, which equals 48. So we just found the slope of the secant line to be 48, which is the average rate of change. In doing a story problem, the answer to the f of b minus f of a over b minus a, the label here, just what's the label on the y-axis? What's the label on the x-axis? Let's say that this was the number of people entering a movie theater. This would be the time, maybe in minutes, and this would be people over here. Well, then the answer that we found would have been people per minute. So just think about what's your label on the y's over the label on the x's. All right, see you next time.